Welcome to a slow, beginner-friendly lesson on hashing files, made for absolute beginners. Files next. Last lesson you hashed a string. Today you hash something bigger, an entire file. A photo. A zip archive. A database backup. A 10 GB movie. Any file, no matter how large, can be reduced to one fixed length fingerprint using hashlib. We learned to read the file as bytes, feed those bytes to SHA-256, and verify the result against an expected hash. This is how the cloud proves your downloads arrived intact and how security teams detect tampering. Bigger fingerprints. Why hash files instead of strings? Because files are big, expensive to move, and easy to corrupt. When you download a 5 GB installer, you want proof that every byte is what the publisher shipped. A hash gives you that proof. Hashes also identify duplicates. Two files with the same hash are the same file, which is how cloud storage deduplicates backups. And content address systems like Git and IPFS use the hash itself as the file's name. Why hash files at all? To hash a file you first need its bytes. Open the file in read binary mode, that is the lowercase rb. Read binary returns bytes, not text, which is exactly what hashlib wants. Read the whole file into a variable called data, then pass data to SHA-256, then call hexdigest. For a small text file this works perfectly. For a large file we will do something smarter in a moment. Read binary, here is a clean function. Hash file takes a path, opens at read binary, reads all the bytes into memory, and returns the SHA-256 hex. Call hash file of notes.txt and you get the fingerprint. This works for any file small enough to fit comfortably in memory, text files, small images, config files. For anything larger we need a different approach. Small files. Here is the problem with reading the whole file. If the file is 10 GB and your laptop has 8 GB of memory, calling read tries to load all 10 GB at once. Your operating system starts swapping, your program may slow to a crawl, and you might crash with memory error. Hashing should never need more memory than the file itself. The solution is to read in chunks, small bytes of the file at a time. Memory is finite. Strings are not the only thing you can hash. Any file on disk, a photo, a zip, a database, has a fingerprint. Files leave marks too. Here is the chunked pattern. Create an empty hasher. Open the file read binary. Loop, read a small chunk, say 8 KB, feed it to update, repeat until read returns nothing. The walrus operator : assigns the chunk and tests it in one go. The hasher keeps a running state internally, so chunk by chunk the final hash builds up. Memory stays tiny, just the chunk size, no matter how huge the file is. The chunk pattern. What chunk size should you use? Common values: 4 KB is conservative, small memory, more reads. 64 KB is a common default, a good balance. 1 MB is good for very large files, fewer reads, slightly more memory. The trade-off is simple: bigger chunks mean fewer disk reads but more memory per chunk. 64 KB is a safe default for almost any file you will hash on a laptop. Pick a sensible size. Watch how update builds the hash. Start with an empty SHA-256 hasher. Call update with chunk 1, the internal state changes. Call update with chunk 2, the state changes again. Call update with chunk 3, and again. The final hexdigest is exactly the same as if you had concatenated all chunks into one giant string and hashed it in one go. Update is just a memory-friendly way to feed data into the same algorithm. Update builds it up. Always use read binary mode when hashing. Text mode, plain lowercase r, tries to decode the file as text, which fails on photos, zips, or any binary data. Worse, on Windows text mode silently translates new lines, which changes the bytes and produces a different hash from the same file. Read binary skips all translation. You get the raw bytes exactly as they are on disk, which is what hashing needs. Bytes stay intact. You cannot load a 10 GB file into memory all at once. You read it in small bytes, hashing as you go. Small bytes, big file. Here is the real use: verifying a file. Verify file takes a path and an expected hash, computes the actual hash, and returns true if they match. This is exactly what you do after downloading a Linux ISO or a software installer. The publisher publishes the expected hash, you compute the hash of your download, and the comparison tells you whether the file is intact. A mismatch means corruption or tampering. Throw it away and download again. The verdict matters. Your operating system already has hashing tools. On Mac OS and Linux, SHASM with -256 prints the SHA-256 of any file. On Windows PowerShell, get file hash with -algorithm SHA-256 does the same. The hash your Python computes will match these tools character for character, that is the determinism of SHA-256 in action. Hashing the same file in any language, on any operating system, always gives the same fingerprint. Tools you already have. Where does file hashing show up in cloud work? Verifying downloaded artifacts. Every Linux ISO ships with a published SHA-256. Confirming uploads to S3, which returns an ETag that is often the MD5 of the object. Deduplicating backups. Two files with the same hash are the same bytes, so storage systems store them once. Detecting tampering in deployed packages. And content address storage, where the hash itself becomes the file's name. Git does this, IPFS does this, modern object stores do this. Real cloud work. Here is hashing in the wild on AWS. Get object attributes on an S3 object and you get back an ETag. For small objects uploaded in one piece, the ETag is the MD5 of the object. So if you hash a local file with MD5 and compare to the ETag, you confirm the object in S3 is byte identical to your local copy. This is how upload tools verify they did not corrupt anything in transit. Hashes are not just exercises, they are wired into every cloud storage service. Hashes on S3, here is deduplication in action. Walk a folder. Hash every file. Group files by their hash. Any two files with the same hash have identical content, you can safely delete one. This is exactly how backup tools find duplicate photos on your laptop, how cloud storage avoids storing the same object twice, and how content delivery networks cache efficiently. The hash becomes the identity of the bytes. Same hash, same bytes. The real question is rarely what the hash is. The real question is, does my hash match the expected one? Does it match? Best practices for hashing files. Always open the file read binary, lowercase rb. Use chunked reading whenever the file might be more than a few megabytes. 64 kilobytes is a safe chunk size for almost any case. And the verification itself is just string equality. Compute the hash, compare with double equals to the expected value. A hash mismatch means corruption or tampering. Never trust a mismatched file. Hold these habits. A few pitfalls to avoid. Forgetting read binary causes Unicode decode error the moment you hash a photo or zip. Reading a huge file all at once causes memory error. Always use the chunked pattern for anything large. Comparing hashes case sensitively, hashlib returns lowercase hex, so make sure your expected value is also lowercase, or normalize both sides. And never trust MD5 for anything security related, SHA-256 is the modern default. Watch your step. Recap. Open the file read binary. Read it in chunks, feeding each chunk to update on a SHA-256 hasher. When the file is exhausted, call hexdigest to get the file's fingerprint. Compare it to an expected hash to verify integrity. The same pattern works for files of any size, from a few bytes to many gigabytes. Chunk, update, hexdigest. In one breath, files have fingerprints too. Open read binary, read in chunks, update the hasher, read hexdigest. Verify downloads by comparing the computed hash to the published one. The same idea powers S3 ETags, Git commit IDs, IPFS content addressing, and every integrity check on the internet. Hashing strings and files is the foundation. Files have fingerprints. Next we apply hashing to passwords. You will learn why plain text passwords are catastrophic, what a salt is and why the same password must never produce the same hash, why password hashing is deliberately slow, and how to use Python's built-in PBKDF2_HMAC to hash and verify a password safely. The stakes go up, but the ideas are the same hashes you already know. Passwords next. If you want practice, copy the hash file function and run it on a real file you own, a README, a photo, anything. Note the hash. Then open the file in an editor, change one character, save, and hash again. The whole fingerprint changes. That is the avalanche effect on a real file. Now undo your edit, save, hash a third time, the hash is back to the original. Determinism in action. Try it on a real file. Think of file verification as a pipeline with a verdict at the end. You open the file read binary. You read the first chunk and update the hasher. You read the next chunk and update again. You keep going until the file is exhausted. You call hexdigest to read the final fingerprint. Then you compare that fingerprint to the expected one, and the verdict is either match or mismatch. Every verification tool on earth runs this same pipeline. The pipeline ends in a verdict. Thanks for learning file hashing. Next we protect passwords. See you on passwords.